Hello all. Today myself and my friend Padmaja will be presenting on optimizing coverage in wireless sensor networks using graph neural networks combined with deep reinforcement learning (DRL). So basically we'll start with our introduction. What is WSN? WSNs are basically wireless sensor networks. WSN consists of spatially distributed sensor nodes that actually collect and transmit the environmental data. WSNs are helpful in various applications such as defense, industrial information, automation, environmental monitoring. And it also becomes challenging to achieve optimal coverages in WSN, especially in the dynamic environment where the sensor nodes continuously must adapt to the changing conditions, mainly the node mobility, that is continuous movement of the nodes and variance of the energy levels. So the existing optimization methods such as PSO, particle swarm optimization, and generic algorithms and modern machine learning models are struggling to handle the dynamic nature of the real world WSN. So these methods often fail to adjust the node placement exactly in the real time. So that will be resulting in suboptimal coverage and inefficient energy use. This actually leads us to a gap, and our research proposing a hybrid reinforcement model and graph neural network integration framework which actually integrates both GNN and DRL, which creates a framework which satisfies this goal. So, in a broad view, DRL basically introduces a real-time reward-driven adaptability, it enabling the sensor nodes to learn optimal repositioning strategies through the continuous interactions with the environment. And apart, meanwhile, the other GNNs provide a powerful mechanism that will encode and utilize the spatial structure and topology of the sensor network. And these GNNs actually what they does is they capture the node-to-node relationships and the resource constraints more effectively than any other flat vector-based representations. The framework's ability to learn and adapt over time, combined with its strong spatial reasoning, makes this framework a significant advancement over any other existing machine learning models. And next, research objective. The main objective of this research paper is to integrate both DRL and GNN to uh, to get the optimized dynamic sensor node placement in the wireless sensor networks that will achieve the most optimized coverage efficiency, energy efficient, and reduce the overlapping. And the problems addressed by our proposed hybrid model improves the coverage efficiency, energy, and also reduces the overlapping nature of the nodes. Also, it ensures the real-time adaptability to the continuous changing of the network conditions. Okay, so these some of the major discussions that are there in the research paper are theoretical background of DRL, theoretical background of GNN, how they are getting integrated. Now we will discuss about all those major discussions. Basically, DRL is nothing but a deep reinforcement learning. It is a powerful machine learning approach where an agent learns by interacting with its environment and using its own feedback to improve its decision making. So the main strength of DRL lies when it's in dynamic situations where the conditions continuously changes, keep changing. So DRL basically empowers autonomous systems to make the real-time decisions. And based on the feedback that they get and learning to the continuous trial and error method that will maximize the rewards over time. Actually, there is an agent called DRL agent which observes its state and then it takes an action and gets a reward. So with each iteration, it refines its own strategy using two methods. One is Q learning and one is policy gradient. So in the coming to the context of WSN wireless sensor networks, DRL basically helps to optimize the exact placement of the sensor nodes by constantly adjusting the node positions. So, based on the live network conditions, and finally, it will achieve the optimized node placement. So, That's the basic theoretical background of DRL. And coming to the theoretical background of GNN, GNN is graph neural networks. These are specialized type of neural networks which are basically designed to handle graph structured data. In the structure, nodes are present represent the entities and like sensor nodes, and the edges represents the relationship between these nodes. So the GNNs work by updating the node's features based on the information that is being gathered from its neighboring nodes, effectively capturing both the spatial relationship and the overall network topology. So this is especially valuable in understanding how nodes are getting connected to each other, and that can greatly influence the exact placement of the nodes based on the performance. So by modeling interactions between the nodes, GNN help to make smarter decisions for exact positioning of the sensor to achieve the maximum optimization. So this is basic theoretical background of GNN. Now the main part, creating a framework out of integrating both DRL and GNN. So the integration of both of the networks creates a powerful synergy that basically enhance the decision making in wireless sensor networks. Coming to DRL, it brings out the adaptability while GNN contributes to the spatial awareness by modeling uh, node relationship. Together, they enable real-time adjustments to the dynamic network changes. Basically, GNN helps the DRL to refine its sensor node placement by understanding the entire network's topology. This combined approach not only reduces the redundant coverage but also ensures more energy efficient use and better network performance. And essentially, GNN processes both global and local node information that will basically allow the deep reinforcement learning to make well informed and optimized actions that will lead to a optimized smarter more responsive WSN management that will be helping us to achieve the more optimization all the aspects of metrics that we want to achieve. So this is the basic discussions about DRL, GNN, and their integrations. Now coming to the model architecture. Now we'll be having an overview of our model architecture. The DRL GNN model is basically built to optimize the exact sensor placement by blending spatial awareness with adaptive learning. It all actually starts with the sensor nodes that are randomly placed in the network and their interactions based on the spatial proximity. As we can see in the figure 1, these nodes communicate and reposition themselves to improve the coverage. The DRL agent is actually responsible for continuously adjusting these nodes' position using real-time feedback to enhance the performance. And a reward system is there which basically guides this process by reinforcing only the most efficient positions or the placements of these nodes. At the same time, the other side, GNN layers capture the spatial relationship between these nodes, enabling the decisions of the DRL and awareing of the network's topology. This integrated approach will definitely effectively mimics the real world scenarios and making the system highly responsive to the dynamic changes in the environment. So we'll discuss more about the data flow and how the data flows in the architecture in the coming slides. As we discussed about the DRL agent and reward system, we'll dig deep into this agent and reward system, how they work. The DRL agent is nothing but deep reinforcement learning agent is basically responsible for optimizing the sensor placement based on real-time feedback of the environment. It begins it actually begins by analyzing the exact current state of the network, which includes the positions, the energy levels of the sensor nodes. Based on this, it takes actions adjusting the node positions to enhance both the coverage and the energy efficiency. And to evaluate how well this agent performs, we have a reward function that is being used. This reward function, increases coverage while reducing the overlap and the energy usage. and the reward function is actually calculated using the formula that has been shown in the slide. So basically, this equation, what it does is it ensures that only the efficient and the balanced configurations of these placements have been considered, and guiding the agent to make more decision that basically improves the performance. Now we will discuss about the how the data flows in the model. So the figure 2 clearly illustrates the data flow and actual interplay between the DRL agent and the graph neural networks. So this interaction is basically the heart of the model's complete adaptive intelligence. The DRL agent begins by assessing the network's current state, which includes sensor node positions, as we discussed, coverage levels, energy consumption, all these metrics. This state information is now passed to the GNN. So the GNN now processes this data given by the agent, and it also focuses on its spatial relationship between the nodes and how they interact, how they are connected, and it performs the next step called message passing between the neighboring nodes to update the node features by capturing both local and global features, topological structures of the network. So once the spatial dependencies are fully understood by GNN, the GNN refines this information and then it sends back to the DRL agent. So using this enhanced data that has been received from GNN, the now the DRL agent will again can make more informed decisions. It decides how and where to reposition the nodes to get the optimum results. So, and in order to improve the coverage and minimize the redundant overlapping and increase the efficiency. So, this updated configuration is now implemented in the network, which leads to a new state that is being generated. And again, this new state will be going into GNN, and the GNN will be sending information back to the uh, DRL agent, and this is a continuous looping process, which help us to achieve this continuous feedback loop enables the system to self improve itself in the real time. So the sensor placement are no longer static or manually tuned; they are completely dynamically adjusted in response to the changing conditions. So this is especially valuable for the large scale networks and decentralized or partially observable networks. So by combining DRL's adaptive learning with GNN spatial awareness, it achieves both robustness and the flexibility. So this is how the data flows from the DRL agent to the GNN back to the agent and how the loop continues. And I think now it's time for Padmaja to start with the simulation setup and how the data sets, graph representation along with the model training process will
Yeah,
be. Yeah,
yeah.
we'll start.
In this slide, we are discussing about the simulation setup. The model was developed and simulated using MATLAB. Key hyperparameters include a learning rate of 0.001, a batch size of 64, and a discount factor of 0.99 to prioritize long-term rewards. The simulation was run on a system with an Intel Core i5 processor and 16 GB RAM to ensure smooth computation. This setup provides an efficient environment for testing and validating the DRL GNN model. The integration of deep reinforcement learning and graph neural networks brings together the strengths of both learning paradigms to solve the complex problems of sensor node replacement. In wireless sensor networks, DRL offers ability to learn optimal node positioning strategies through continuous interaction with the environment driven by rewards based on the performance metrics such as coverage and energy efficiency. However, DRL on its own lacks a robust way to represent the structural relationship between nodes in a spatially distributed network. This is where GNN plays a vital role. GNN encodes the graph structure of the WSN by treating sensor nodes as graph agent with context about local and global topology, which enhances its decision making ability. The DRL agent uses this context to perform smarter actions such as repositioning nodes to reduce overlap or shifting coverage based on network changes. Next slide. In this slide, the data set, we are discussing about the data sets and the graph representations. For training and testing, the model uses synthetic datasets that simulates real-world network behavior. These datasets include randomly placed sensor nodes and energy consumption data to mimic realistic conditions. This setup allows us to evaluate the model's performance under different network configurations. In terms of graph representation, each node corresponds to a sensor location containing position and energy details. Edges represent the communication links between neighboring nodes. This graph-based structure enables the model to capture spatial relationship accurately, which is essential for optimizing node replacement and overall network efficiency. Next slide. In both the slides 15, 16, we are discussing about the model training and algorithm. It includes total 5 steps. The first step includes random node replacement, which is an initialization. The training process begins by initializing the wireless sensor network through random node replacement. This step creates a starting point for the agent to learn from with nodes placed arbitrarily across the monitoring area. It provides a diverse range of configurations, allowing the model to learn under various spatial distributions and energy scenarios. These random placements also simulate real world deployments where manual fine tuning of every node may not be practical. In step 2, the Q learning for placement optimization. Once initialized, the model uses Q learning, a reinforcement learning technique that helps the agent evaluate the outcomes of its actions over time. The DRL agent learns a Q value for each state action pair, which reflects the expected reward. By exploring various node replacement adjustments and observing the resulting coverage, energy usage, and overlap, the model gradually improves its strategy. Over many episodes, Q-learning helps discover efficient node arrangements that yield higher cumulative rewards. And in next slide 17. In this slide, we are going to discuss about the reward function evaluation, that is step 3. The next phase involves calculating the reward for each node action. The reward function incorporates 3 key factors: coverage, overlap, and energy consumption. It is defined as the below formula. This mathematical formula allows the agent to understand which placements are beneficial and which are not. If a new node arrangement increases coverage while reducing energy usage and overlap, the agent receives a higher reward, encouraging it to repeat similar actions in future training rounds. And in the fourth step, we are policy how the policy is executed. After evaluating possible actions and rewards, the DRL agent applies its learned policy to reposition the nodes accordingly. This is where the model transitions from theory to action, taking steps in the environment based on what it has learned so far. The movement of nodes is not random anymore. It's driven by calculated decisions. This step helps validate whether the policy learned in simulation translates into meaningful performance improvements when executed. And the last step in 5, the GNN message passing for spatial learning. Finally, the GNN component takes over to enhance spatial reasoning. Through message passing, each node exchanges information with its neighbors, such as position and energy level, to update its own state. This allows the network to understand not just isolated node conditions, but the broader topology. The updated features are sent back to the DRL agent, which then makes better informed decisions. This creates a feedback loop between learning and spatial reasoning, leading to more effective and collaborative sensor replacements. Next slide will be continued by Deepak.
Yeah. Now coming to the results part, basically, this is a slide that explains how the coverage ratio is affected based on the number of nodes and based on the number of iterations. Here clearly we can see our coverage ratio is increasing as the number of iterations increases, because our model is basically completely depending upon learning from its feedback, right? So upon each iteration it will learn from the previous iteration's feedback and it will continuously improve. So obviously our coverage ratio increases as the number of iterations increases, and we can see a significant increase as the number of nodes also increasing. So if we see the dark blue line, which is number, which is having 20 nodes, and the light blue, which is achieving its peak optimization with 50 nodes. So we can easily say as the number of nodes increases, the coverage ratio also increases. So with the 50 nodes, the coverage ratio reaches its highest optimal value. Same with the energy efficiency. As iterations increases, the energy efficiency usage also increases, along with the number of nodes increasing. The highest number of nodes reaches the optimum energy efficiency. Now coming to the overlap ratio, overlapping reduction improves the overall network performance and resource usage. So lesser the overlapping of the nodes improves the higher the network performance. So we want to achieve as much low as overlap ratio possible. So we can clearly see again as the number of nodes and the number of iterations increasing, the overlap ratio is continuously decreasing. So we reach the lowest point or the minimum overlap ratio with the highest number of nodes and highest iterations. So this means we are achieving the optimum network performance and resource usage with this lesser overlap ratio. So and these are the basic comparisons, and now the benchmark comparisons is the coverage ratio comparison with our proposed DRL GNN and the other other algorithms or other models. So clearly we can see our proposed DRL GNN method framework has clearly outperformed the other models such as CNN, DenseNet 50, convolution neural networks, PSO, WOA. All these models have been outperformed by our graph neural networks uh, DRL framework. So clearly it has outperformed all the other models. We can quantitatively see with the numbers how the numbers varied with the other models. Clearly, this table represents the comparison of our proposed DRL GNN with the other models, including CNN, DenseNet 50, PSO, WOA. Coming to the coverage ratio, which is the first thing, DRL GNN, our proposed model achieves the highest coverage ratio of 96.4 percentage, outperforming all the other models you can see. Coming to the energy efficiency, our model is achieving 95.8%, outperforming all the other models. And now the overlap reduction. As we know, lesser the overlap reduction, more the performance in the network. So we need to achieve the least overlap reduction that have been achieved by our model as compared to the other models. And coming to the latency also, lower the latency indicates the faster processing and faster decisions time for decisions. So the lowest latency also has been achieved by our model. So comparing the quantitatively also our model is performing. So, and this is the statistical analysis of how many times after the multiple trials, how much is the deviation mean of each and every metrics, that is coverage ratio, energy efficiency, overlap ratio, and latency. Everything has been given in this table. So this is the basic comparisons and of all the metrics basically with other models and basically with the number of nodes and the iterations. All these comparisons have been discussed here. So I think now Padmaja will be concluding this, and yeah, go ahead, Padmaja. Yeah, and we can conclude this like basically in conclusion, the proposed model DRL GNN, it basically demonstrates the significant improvements or all the other traditional methods in terms of all the metrics coming to the coverage, energy efficiency, overall overlap reduction, latency, everything, providing a more and efficient solution for our dynamic sensor node placement in the WSN networks. So also the result of highlights that the DRL GNN superior performance uh, in this aspect of optimizing the network efficiency and the resource usage. And also the future work will definitely focus more on enhancing the model's computational efficiency that will definitely support the large scale networks. Um, and conducting real world testing that will definitely key to evaluate its scalability and robustness in practical applications in the real world scenarios. And coming to the references, this is the link to the research paper that we have referred to prepare the report and the presentation. Thank you from my side and Padmaja. Thank you.
Stop in the